Today we're going to be looking at section 3.6, which is on multiplying matrices. So when we look at multiplying matrices, we have to keep in mind these two things. So the product of two matrices, A and B, is defined provided that the number of columns in A is equal to the number of rows in B. So if we take the first matrix, however many columns are in that one, has to be the same as the number of rows in the second matrix. And then second, if A is an M by N matrix and B is an N by P matrix, then the product of AB is an M by P matrix. So notice here, the first statement tells us that there's our N and here's our N. Those two must be the same. So if we have an M by N and an N by P, those two are the same, so we can multiply them. If that is the case, then our answer is going to be an M by P matrix. So if we look at example 1, we have a 3 by 5 matrix and a 5 by 2 matrix. So here, the columns in A is the same as the rows in B. So we can multiply these two, and the result will be a matrix that is a 3 by 2. If we look at B, notice here in matrix A, that's a 3 by 4 matrix. Matrix B is a 3 by 2 matrix. The columns in A is 4. The rows in B is 3. They are not the same, and so this one is not defined. We cannot multiply those two because the columns in A is not the same as the rows in B. So if we look at the guided practice questions on page 195, they're going to ask you to do those two and find out what the result matrix is if it can be defined. So turn your books to page 195 and go ahead and do those two guided practice questions. You can hit pause when you're ready, and then hit play when you're ready to resume. So if we look at these two guided practice questions, number 1 will end up being a 5 by 2, and number 2 is not defined because the columns in A are not the same as the rows in B. All right, now down to multiplying matrices. This is very, very different than adding or subtracting matrices, or even multiplying by the scalars like we did the other day in section 3.5. We want to find the element in the ith row and the j column of the product matrix, AB, and then multiply each row in the ith row of A by the corresponding element in the jth column of B. Then add the products. Now, that sounds pretty confusing. So here, we're going to write it out. So we have A, B, C, D for matrix A, and then E, F, G, H for matrix B. So we're going to multiply these two. So essentially what we're going to do is we're going to take and we're going to go across the column in the first one, or across the row in the first one, down the column in the second one. So we're going to multiply row 1 with column 1. So row 1 in A is A, B, and column 1 in B is E and G. So we're going to take A times E, and then we're going to go B times G. So again, we always are going to go across the rows in the first one and down the columns in the second one. So that is going to be our element for row 1, column 1. Now we're going over to row 1, column 2. So now I'm talking about row 1, column 2. So it's going to be AF plus BH. So we'll erase that. But it's going to be AF plus DH. So now we go to row 2, column 1. Again, we go across, so it's going to be CE, and DG. And then we're going to go across and down. So it's going to be CF plus DH. And so that's how we would do the multiplication of two matrices. So let's look at example 2. In example 2, we're going to start with matrix A being 2, negative 3, 1, 5. And B is going to be 1, negative 4 in row 1, and 3, negative 2 in row 2. So once again, we're always going to go across the rows in the column A, or across the rows in matrix A and down the columns in matrix B. So when we go for AB, the product is going to be 2 times 1 plus negative 3 times 3. That's row 1, which is right here, and column 1, which is right here. We're multiplying those two. Now we go row 1, column 2. So it's going to be 2 times 1, or column 2, sorry. It's going to be 2 times negative 4 plus negative 3 times 2. Again, across the first one, the first column, or the first matrix, down the second column in the second matrix. Now we go to row 2, column 1. So it's going to be 1 times 1 plus 5 times 3. And then we go to row 2, column 2. So it's going to be 1 times negative 4 plus 5 times negative 2. And so now we're just going to simplify this. Well, it's going to give us 2 minus 9, and this one's going to give us negative 8 and a minus 6, 1 and a 15. So 1 plus 15, negative 4 minus 10. And so the answer we should get when we multiply these is that. We should get a matrix that is negative 7, oops, I forgot. This should be a negative 2 right here. Right there, that should have been a negative 2, which would have made this plus 6. So this one then would be negative 8 plus 6 is negative 2. And then 16 and negative 14. So there is our matrix. Again, anytime that we're multiplying, we're going across in the first matrix. We're going to go the row times whatever the column is. So let's do guided practice question number 3 in your book. And I'll go ahead and write this up here quick. So A, the A matrix is negative 3, 3, 1, negative 2. And the B matrix, which we're going to multiply, is 1 and 5, and negative 3, and negative 2. So go ahead and multiply those two matrices. So go ahead and hit pause, and then you can hit play when you're ready to move on. And here is the answer for your guided practice question number 3. So example 3, we're going to use matrix operations. So use the given matrices and evaluate the expression. So there are the three matrices, and we're going to go B minus C times A. So we're going to go A times B minus C. Well, I'm going to do the B minus C first. So I'm going to write my A here. So it's 3, negative 2, 0, 4, negative 1, 5. And then we can do B minus C in our head. So 2 minus 2 is 0. Negative 3 minus 1 is negative 4. 1 minus negative 4, that's 1 plus 4, which is 5. And 0 plus minus negative 2, which is 0 plus 2, which is 2. So this matrix is a 3 by 2 matrix. This matrix is a 2 by 2 matrix. So we notice that those rows and the columns in the first one, are the same as my rows in the second one. So I can multiply these two. And again, we're going to go across and then down. And notice our matrix is going to end up being a 3 by 2 matrix. So we're going to go row 1 and column 1. So it's going to be 3 times 0 plus negative 2 times 5. And then 3 times negative 4 plus negative 2 times 2. Then row 2 and column 1. Well, it's going to be 0 times 0 plus 4 times 5. And then it's going to be 0 times negative 4 and 4 times 2. And then we're going to go row 3 in column 1, which would be negative 1 times 0 plus 5 times 5. And then negative 1 times negative 4 and 5 times 2. And so if we do that, we're going to have 3 and negative 10, which is negative 7. Oh, actually, 0. Sorry, 3 times 0 is 0. And negative 10 is negative 10. We're going to have negative 12 and a negative 4. So that's going to be negative 16. We have a 0 and a 20, so that's going to be 20. We have a 0 and an 8, so that's going to be 8. And we have a 0 and a 25, which is going to give us our 25. We're going to have 4 and 10, which is 14. So there is our matrix. Okay. Now, that is going to be the answer that we get for both A and for B. If we would do that one as well, we would get the same answer. Notice this is just the distributive property, AB minus AC. So if we were doing B, we would multiply matrix A and matrix B together. Then we would multiply matrix A and matrix C together. So that means it would require us to do 2 different multiplications. And then once we got each of those answers, we would subtract them. Well, obviously, A is going to be quicker to do because we only have to do 1 multiplication there. We're going to do the subtraction first, then we're going to do the multiplication. So let's look at the properties of multiplication. It says let A, B, and C be matrices and let K be a scalar. The associative property of matrix multiplication, that one works. We can multiply those matrices, A times B times C or AB times C. Okay, it doesn't matter how we group them. Now the left distributive property works. So if I have A, I can take A times whatever the answer is for B plus C. Or I could do like we just did above, A times B plus A times C. The right distributive property works. Okay, if I have C as my last matrix, I can multiply A and B first, or add A and B first, multiply by C. Or I can multiply A and C and multiply B and C and then add them. The associative property for scalars works. So I could multiply matrices A and B and then multiply K, or I could take K times each one and then multiply it by one of them and then multiply it to the other one. Now notice the commutative property does not work. We cannot switch the order at which they work, because if we have a 2 by 3 matrix and a 3 by 4 matrix, we can multiply these to get a 2 by 4 matrix. But if we switch the order, this becomes a 3 by 4 and a 2 by 3, and now we cannot multiply those because the number of columns in A would no longer be the same as the number of rows in B. So the commutative property does not work for the multiplication of matrices. So let's go down to question number 4, 5, and 6 in the guided practice, and those are on page 197. And go ahead and pause the video as you do those. And here are the answers to the guided practice questions 4, 5, and 6. Notice once again that 4 and 5 you'll get the same answer because the distributive property of subtraction is possible in multiplication of matrices. And then number 6, we multiplied by a scalar. So the next thing we're going to talk about is the cost matrix. And the matrices multiplication is useful in business applications because an inventory matrix, when multiplied by a cost per item matrix, results in the total cost matrix. So we're going to look at the inventory matrix. And we're going to multiply this by the cost per item matrix. And that is going to give us the total cost matrix. So if you look at page 198, we're going to go through that example in the book. So it says it has 2 hockey teams that submit equipment lists for the season. Okay, you have a women's team there and a men's team. So it says that the sticks are $60, each puck is $2, and each uniform is $35. We're going to use the matrix multiplication to find the total cost of equipment for each item. So if we write these matrices out, notice the first one is my inventory matrix. How much do I need? So for the women, I need 14 sticks, 30 pucks, 18 uniforms. For the men, I need 16 sticks, 25 pucks, 20 uniforms. So that's my inventory matrix. The next one is the cost per item matrix. Well, how much were they? Well, it's $60 a stick, $2 a puck, $35 for a uniform. And so now we are going to multiply those, and that'll give us the total cost matrix. How much do we pay for the women? How much do we pay for the men? So again, across in the first matrix, down in the second matrix. So we're going to go ahead and multiply those. So if we take our 14 times 60, oh, that does not look like a very good 60. So 14 times our 60, and then our 30 times 35, and our 18 times 35. That should have been 30 times 2. So 30 times 2 and our 18 times 35. Then we're going to do the same thing with the men. So it's going to be 16 times 60, 25 times 2, and our 20 times 35. And then when we add all of those up, so do the multiplications, add them up, we're going to end up getting 1,530 and 1710. So now what we're going to do is we have to answer the question there. It says, use a matrix multiplication to find the total cost of equipment for each team. So the women's team spent $1,530. And the men spent $1,710. So that is how we used cost matrices to find out total expenses. So section 3.6, we talked about multiplying matrices. So again, the first thing we have to do is we have to check, can we actually multiply these matrices? To do so, the number of columns in A must be the same as the rows in matrix B. And then we would multiply those across the rows in the first column, down the or in the first matrix, down the columns in the second matrix. So row 1, column 1, we'd multiply all of row 1 with all of column 1, add those up. And then we looked at cost matrices as well. So your homework assignment for section 3.6 is listed below.